Humanity has long dreamed of one day venturing beyond our solar system and freely exploring the vast unknown of the universe. To make that dream a reality, we would need spacecraft capable of traveling close to the speed of light. However, according to our current understanding of physics, no object with mass can travel faster than light, no matter how advanced our technology becomes. So, does that mean interstellar travel will forever remain an impossible dream? Not necessarily. One physicist proposed a radically different concept for space travel, one that could, in theory, make faster-than-light travel possible without violating the laws of physics. He even worked through the mathematics using Einstein's general theory of relativity and published the results in a scientific paper. That concept is the warp drive, made famous by Star Trek. But is the warp drive nothing more than science fiction? Or is it actually grounded in real physics? In today's episode of Dr. Sci-Fi, we'll explore the science behind the warp drive and see if humanity could one day turn this concept into reality. So, let's get started. First, let's break down why faster-than-light travel is considered impossible in the first place. According to modern physics, the faster an object with mass moves, the more energy it takes to accelerate it even further. Eventually, reaching the speed of light would require an effectively infinite amount of energy, making it physically impossible. This is one of the fundamental conclusions of special relativity. But energy isn't the only problem. Special relativity also predicts a phenomenon known as time dilation. As an object approaches the speed of light, time passes more slowly for those on board than it does for an outside observer. Imagine traveling to a distant star at nearly the speed of light and then returning to Earth. While only a few years might pass for the crew, hundreds or even thousands of years would have passed back on Earth. In other words, even if we built a spacecraft capable of traveling near the speed of light, its crew would never be able to return to the Earth they left behind. Then there's another major challenge, surviving the journey itself. Even if we somehow overcame all of these physical limitations, a spacecraft would still have to accelerate to near light speed. To reach those speeds within a practical time frame, it would need to accelerate rapidly, producing enormous g-forces that would almost certainly exceed the limits of the human body. Even fighter pilots flying at supersonic speeds require specialized training and g-suits to withstand high g maneuvers. The forces required to accelerate a crewed spacecraft to relativistic speeds would be on an entirely different level. In the end, as far as modern physics is concerned, not only is faster-than-light travel impossible, but even interstellar travel at speeds close to the speed of light poses staggering challenges. That's why faster-than-light travel has long been regarded as nothing more than science fiction. But surprisingly, the idea that might overcome these limitations first appeared in science fiction: the warp drive. The warp drive was first introduced in Star Trek, which premiered in 1966. Unlike conventional rockets that accelerate the spacecraft itself, a warp drive operates on an entirely different principle. It manipulates the fabric of spacetime. The basic idea is surprisingly simple. If spacetime in front of the spacecraft is compressed while spacetime behind it expands, the spacecraft itself doesn't have to move through space at all. Instead, space itself moves, carrying the spacecraft to its destination and effectively allowing it to travel faster than light. This region of distorted spacetime surrounding the spacecraft is known as a warp bubble. In Star Trek, the iconic visual effect of stars stretching into long streaks is a cinematic representation of this distortion of spacetime. As surprising as it may sound, this idea isn't entirely science fiction. Even today, the universe is expanding, and because space itself is stretching, extremely distant galaxies are receding from us faster than the speed of light. In other words, the core concept behind the warp drive, traveling by manipulating spacetime rather than moving through it, isn't entirely disconnected from real-world physics. Even more remarkably, it offers a way to overcome many of the fundamental obstacles that make conventional faster-than-light travel seem impossible. First, the warp drive doesn't violate Einstein's theory of relativity. Relativity states that the speed limit applies only to objects moving through spacetime, not to the expansion or contraction of spacetime itself. If the spacetime surrounding a spacecraft could be made to move, the spacecraft would never need to travel faster than light on its own. Instead, it could reach its destination through the expansion and contraction of space itself. It's like standing on an escalator. You're standing still, but the escalator carries you forward. The warp drive could also potentially overcome the problem of time dilation. Because the spacecraft itself is not actually traveling faster than light, the crew would experience the normal passage of time. And since the spacecraft remains essentially at rest inside its own warp bubble, its occupants wouldn't have to endure enormous acceleration or crushing g-forces. In theory, faster-than-light travel could even provide an exceptionally smooth ride. From the perspective of modern physics, the warp drive is a remarkably elegant concept, one that could, at least in principle, bypass many of the fundamental challenges associated with conventional faster-than-light travel. Ironically, the creators of Star Trek have said that the warp drive was never intended to be based on real scientific principles, but that all changed in 1994 when one physicist decided to take the idea seriously. Dr. Miguel Alcubierre, a physicist at the National Autonomous University of Mexico and a lifelong Star Trek fan. Inspired by Einstein's theory of relativity, Alcubierre set out to investigate whether a warp drive could actually work. This pursuit culminated in his landmark 1994 paper, The Warp Drive: Hyperfast Travel Within General Relativity. So what did the math actually say? Did it really show that the warp drive from science fiction could become reality? Alcubierre incorporated the geometry of a warp bubble into Einstein's field equations to determine whether such a form of travel was mathematically possible. Remarkably, the answer was yes. His calculations showed that a warp drive is mathematically consistent with Einstein's theory of relativity. In other words, Alcubierre mathematically demonstrated that if a warp bubble could somehow be created, it would be possible to distort space-time around a spacecraft, allowing it to travel dozens of light years in a very short time. On paper, at least, the concept was possible, but that was where the real problem began. As Alcubierre continued his calculations, he discovered that maintaining a warp bubble would require a highly exotic form of energy, something unlike any matter or energy ever observed. It's called negative energy. Everything we encounter in everyday life possesses positive energy. As a result, the concept of negative energy doesn't normally appear in classical physics. If the warp drive is ever to become a reality, it would first require an extraordinary form of energy that we still don't know how to generate. Surprisingly though, negative energy isn't just a science fiction concept. In 1948, Dutch physicist Hendrik Casimir predicted, using quantum mechanics, that under very specific conditions, the energy density of a vacuum could actually drop below that of the surrounding space. This prediction became known as the Casimir Effect. Then, in 1997, physicist Steve Lamoureux at Yale University experimentally confirmed the Casimir effect, providing evidence that regions of negative energy density could exist. The problem is that the amount is extraordinarily small. Early estimates suggested that creating a warp drive would require an amount of negative energy far exceeding the mass energy of Jupiter. With today's technology, such a feat remains far beyond our reach, and the hurdles don't stop with energy. Even if we one day learn how to generate negative energy and create a stable warp bubble, another major obstacle remains. We still don't know how to steer a warp bubble or bring it to a precise stop at its destination. Some studies even suggest that a spacecraft inside the warp bubble could be causally disconnected from the warp field itself, making it impossible for the crew to control or deactivate it from within. So, while the warp drive appears to be theoretically possible, actually building one remains a challenge for the distant future. Even so, it remains one of the most compelling concepts for faster-than-light travel, and alongside wormholes continues to be an active field of research in modern theoretical physics. Faster-than-light interstellar travel has been one of humanity's greatest dreams for generations. Just as black holes, once confined to Einstein's equations, were eventually discovered, could the warp drive, an idea permitted by relativity, one day open a new era of space exploration for humanity? The answer lies in the future of science. That brings us to the end of today's story. I'll be back next time with another fascinating topic from the world of science. This has been Dr. Sci-Fi.